Hi, I'm Harshit Patni, roll number 201501101107, and I present to you the project report for the phase 2 of Science 2. So, my assigned molecule was 3DNL underscore A.pdb. All the code that was used to run the project is available through this drive link. Till phase 1, I have generated a GI of trajectory of an SMD visualization, simulated visualization in VMD. So these were the steps that were used to create a GIF trajectory in the phase 1, and I'll skip this. Now I'll tell you about the Jarzynski equality. The Jarzynski equality is an equation in statistical mechanics that relates free energy differences between two states and the irreversible work along an ensemble of trajectories joining the same states. In thermodynamics, the free energy difference del F between two states A and B is connected to the work done W on the system through the inequality del F is less than equal to W, with equality holding only in case of quasi-static process. That is, when one takes the system from A to B infinitely slowly, the equality is obtained from another known theorem such as Crookes fluctuation theorem, and the equality is as follows: e to the power minus del F by kt equal to e to the power minus average of W by kt, where average of W by kt is the average work done over all the trajectories. The equality is given by exponential of minus of del F by t equal to average of exponential of minus Wt of t. Similarly, for the reversible process, the equation can be written as this, where the right hand side can be expanded in terms of so-called cumulants. So the difference del F equal to average of Wt minus 1 by 2t into variance of Wt, where cumulants up to the second order are shown. The PMF estimation is done using three different forms. First is using FEXP, which is equal to minus T log average of EXP minus WT by T, the exact form. Second is F1 equal to average of WT, which is known as first order cumulant. And the third is F2 equal to average of WT minus 1 by 2T into variance of WT, which is known as second order cumulant. The script used to calculate the estimates and stored as the cumulants.tcl. Finally, all the three estimates are plotted together on the same plot. Now I will run through the steps that were used in phase 2 of the project. After generating the trajectory of the system, analysis of SMD trajectory is done. Since the Pulling velocity of trajectory is very high, and thus we reduce the velocity of generating new trajectories. So after generating three trajectories, we store the we generate the three trajectories with the velocity of 0.01 angstrom per picosecond are stored in a file called da.dat. Each trajectory is present in the d_smd_tcl.out file. Each trajectory has 20,001 lines as the total time is 100 picosecond and time step is 0.1 picosecond. For making da.dat files are combined using a SQL script. Loading the trajectory into VMD and running our loadtraj.tcl script was used, and row numbers range from 1 to 20,001, and the script defines some variables. Now coming on to the plot, the first plot was made using the script plot extension time.tcl, which creates 2D graph with x-axis as time and y-axis as extension between the constraint points. The constraints in the smd.tcl fix the initial position of atom at origin and pulling atom at coordinate 0, 0, 13, which means that the initial distance between the atoms is 13 angstrom. For the next plot, force against extension for all trajectories, the script plot force extension.tcl was used. For calculating the work done, we run the following commands in the tk console of the VMD, and after that the work done is calculated using the script calc_work2.tcl, and the plot is made using plotw.tcl. The graphs that were obtained is the first graph of extension against time, as seen through the graph is almost linear in time with y-intercept as 13 the initial distance. Second graph is the plot of force against extension and shows the fluctuation in the force. The plot of work done against extension shows the maximum range is about 150. The final curve is free energy PMF versus extension, and now I will compare my work with other people. First is extension versus time. So this was the graph obtained by Harshit Mahajan, and this was the graph obtained by Satyam Mittal. The extension versus timestamp is linear for Satyam Mittal's molecule, whereas in Harshit Mahajan's molecule and my molecule the distance is linear with the time, but there are some fluctuation. Second graph is between force versus extension. The first graph is of Mahajan and second graph is of Satyam Mittal. The force versus extension curves are almost the same for Mahajan and my molecule. Satyam has plotted his molecule by scaling the axis, thus this plot appears to be zoomed in. Third graph, work versus extension. First is Mahajan's plot and second is Mittal's plot. The work versus extension shows a uniform relation in case of Mahajan's molecule and is almost the same for two trajectories in his molecule, but Satyam's molecule shows fluctuation in the trend. Fourth and final one is the PMF calculation. The Harshit Mahajan's graph and Satyam Mittal graph are obtained as follows. The PMF in the case of Satyam's molecule shows that exponential linear trajectories are very close, but they are far apart in Mahajan's molecule and my graph. Finally, the inference from the all above graphs is as follows. The change in free energy is the same regardless the path taken, but it can only be equal to work done when it is quasi-static. So if we want the change in free energy, we can only find it through Jarzynski equality. The limit of an infinitely slow process, the work W performed on the system in its realization is numerically the same. So the average becomes irrelevant and Jarzynski equality reduces to thermodynamic equality delta F equal to W. In general, however, W depends on the specific initial microstate of the system, though its average can still be related to del F through an explication of Jarzynski inequality. The three curves in the output are the different approximation of the same Jarzynski equation. Thank you.